something like that. Okay, so let's get back in this. Let's talk about magicalWell. Folks, this is one of my favorite problems. I love this problem. I think this is fantastic. It's going to be a really good one. This is actually going to illustrate a lot of different concepts. So I'm actually really excited about this one. Let's dive in. You are standing at a magical well. It has two positive integers written on it, A and B. Each time you cast a magic marble into the well, it gives you A times B dollars, and then both A and B increase by 1. You have N magic marbles. How much money will you make? Okay, so just a really great question. I really like this one. I think it's very elegant in its simplicity. It's simple yet deep, right? So I think that's really cool. Let's take a look at a few ways of doing this. I want to start with what I would consider sort of the most naive, the most literal interpretation. This is the loop tunnel after all, so let's start with a loop. So we're going to say we'll have this total that we're going to keep track of, and it's ultimately going to be the thing that will return at the end. But in between here, we'll do a little for loop. What are we going to say here? Well, basically, we'll say I is going to start as 0, and it's going to be less than n. Basically, I'm just trying to say, like, this is a loop that's going to fire n many times. That's basically the idea. What are we going to do in this loop? Well, basically, we're going to say total plus equals A times B, right? That's what it does, right? We drop in a marble, we get A times B dollars, and then what happens? Oh, both A and B increase by 1. Okay, so let's do that. So A plus plus, B plus plus. Is that gonna work? There it is. Okay, cool. So I think that's probably gonna pass all the hiddens. We'll find out. Yeah, great. Oh, and you know what? Check it out. Boom! We made it to a new level. But I didn't want to back out of that. Okay, no, let's go back in. We have unfinished business over here. So first of all, I want to try to optimize this loop a little bit. So instead of doing like this operation involving A and B, and then modifying A, and then modifying B, instead of that, I want to do it all in one step. So I'm going to do A plus plus and B plus plus. And now you might be looking at that and thinking, oh, but that's not going to work because you're adding 1 to A and adding 1 to B and then multiplying them. So shouldn't that give you the wrong values? And no, as we can see, it's not giving us the wrong value. So why is that? Well, it's because since the plus plus happens after, that means it's actually going to do the iteration after using the number. If we were to do plus plus A and plus plus B, then it would use the iterated version and yeah, it would iterate and then multiply in that case. So if you're ever confused about that, if you ever get them mixed up, if you're unsure, like which one adds them first or which one iterates it first, well, think about it in terms of order, like just going from left to right. If you see the pluses first, they're going to get done first. If you see them after, they're going to get done after. Okay, and we've got this down to 1 line, so we can probably just put it up here, and yeah, it's getting nice and efficient, succinct, and I believe it's passing all the hidden tests still, so we'll just verify that, and if so, we'll move on. Yeah, nice. And when I say move on, I mean move on to a different solution for this one. So, okay, cool. So we'll call that magicalWell 1, and we'll move on to something else. So what's the next thing I want to look at? Well, we're using a loop here. I'm thinking, hey, if we can do this without a loop, that'd be cool, right? So let's try that. So I'm going to use an array. Specifically, I'm going to use this trick. I've used this one before, but it's kind of weird. It's kind of confusing maybe, so let me know if you have any questions about it. We've done Array.from before, right? Like we can do Array.from with a lot of things. We could have like a string, for example, and that's going to be null because I'm not returning anything, but let's try this. And it's basically just going to take that string and take all the characters. We could also have... well, we can have other stuff in here. There are other iterables, that sort of thing. But specifically what I want to do for this one, this is kind of strange, but we can just have an object and all it has is a length property. An object doesn't normally have a length property, but an array does. So I think this almost sort of like tricks it into giving us an array of that given length. It starts out as all nulls. Now in this case, we want the array length to be n, because that's how many times we're going to be dropping marbles, right? So it's going to be n, and then we can give this a second argument, and it's going to be a function. So I'm going to use an arrow function. V and I stand for value and index. The reason I'm using both of those arguments here is specifically because the index is always the second argument. I don't plan on using v at all. I'm not going to use the value because they're all nulls anyway. So we're not really going to use this at all, but we need to include it so that we can actually get to this one. That's basically the idea here. Okay, and what are we going to put in here? Well, basically it's going to be, this is where we're doing our a times b, right? But the thing is, that value is going to change each time. So we could either have something that's going to be like iterating A, iterating B, or we could do something like A plus I and B plus I. So let's try that. We'll see what we get. Okay, so we get 2 and 6. Those add up to 8. So that's good. That one's just 1. What do we have here? 30, 42, 56. Well, I trust that adds up to 128. Not a great mental math guy, but yeah, I believe it. Okay, so is this the only way we could do this? I'm wondering actually now, do we actually need the I? Like, if we were to modify A and B each time here, would that work? Or is it going to be like, is it going to create the array and then do the iterations? I'm wondering. Huh. Oh, hey, look at that. Huh, it works. Well, that's probably better, right? Because we don't need to actually put any arguments in here. Ooh, that's great. Okay, but we don't want, we're not done yet, because we don't want just like an array of these numbers. We want all of these added up. We want the sum. So we're going to do a reduce. Keep in mind, a reduce is going to take in a function with 2 arguments. Well, there are lots of ways of doing reduce. It could have more arguments than that, but by default, we usually use a function with 2 arguments, and this is like what we want to do with them. So since I want to add all the elements together, I'm doing p plus q. So let's run that. We'll see if that works, and it seems to be working for the sample test anyway. Let's submit it. We'll see if it passes the hiddens, and oh, it doesn't. Okay, why not? Oh, you know what? I think it's probably because, could there be an empty array? Could n be 0? N could be 0. Wow, look at that. N can only go up to 5. Whew. Okay, so n could be 0. If n was 0, this would be an empty array, and I don't think you can do a reduce on an empty array. So maybe we'll just say something like this. N? Right? We could even be more explicit about it and say, n is greater than 0? And if n is greater than 0, it'll do this. Otherwise, it'll just return 0. Let's try that. Will that work? Yeah, okay, so that passes the sample test. Yeah, okay, so that passed the hidden. So we were right. Okay, and we don't technically need that because, like, if it's anything other than 0, then that's going to be considered true. And it has to be, like, greater than or equal to 0. So if it's not 0, it's a positive number, so it's going to work. So let's run that. I think that's, yeah, okay. So that's probably the best that we're going to get in terms of this array strategy. But hey, I'm looking at these arrays and I'm sort of thinking like, well, you're going to put a new array in memory for this. You're going to do a reduce, so you're going to iterate through this array. I'm thinking this isn't really any better than just doing a for loop. In fact, in some ways, I think it's worse because it's taking up the memory of actually having a new array in here. So, I guess I'm not as impressed with this solution in that case. So let's try a different way of doing it. Let's try to find something that's actually going to be like a lot more efficient. That'd be nice, right? Okay, I just want everything on one line there. Okay, here's what we're going to do for this one. So we're going to use the concept of recursion. So recursive function, as you may know, is a function that calls itself. Recursion, I think, now correct me if I'm wrong on this, but I believe recursion is sort of equivalent to loops in the sense that anything you can do using a loop, I believe you can use recursion for it and vice versa. But I might be wrong about that. Maybe there's some special cases, some edge cases I'm not considering, but anyway, as for now, we're going to use recursion. So how are we going to do that? Well, basically what we're going to say is if n is greater than 0, then we're going to keep it going, right? So we're going to say return a times b plus whatever the next iteration is. So what's the next iteration? Well, it's where we call the function itself, magicalWell. We call it again. With what inputs? Well, now a is going to be 1 greater than it was, so a plus 1. B is going to be 1 greater than it was, so b plus 1. And n is going to be 1 less than it was, so n minus 1, because we just spent that marble. Okay, so we're calling magicalWell. And if n is not greater than 0, I guess we'll just return 0 in that case, right? There's nothing much to return there. So let's try that. Will that work? And I guess while we wait for that, we could probably clean this up in a few ways. So first of all, it's saying if n is greater than 0. Yeah, okay, it works. Awesome. So it's saying if n is greater than 0, but again, just like we saw over here, we could just say if n, right? Because if it's 0, that's going to get typecast to false. So, okay, great. And notice in each case, we're just returning something. So maybe we'd be better off using a ternary here. So we could say return n, and then we'll have some condition over here. N is the condition. We'll have 2 possible outcomes. So we'll say either return this over here or return 0. So let's see, is that going to work? Yeah, it does. That's pretty not bad. I think I like that one. I think it's pretty cool. I mean, again, is it better? I don't know. It's tough. It's really close anyway, right? Like, because this has to iterate the same number of times as this. Every time this is going through another iteration of the loop, this is calling the function again. So I think in that sense, they're kind of equivalent. I mean, this one, we're getting into like the call stack, which it's a bit of a foggy area for me, but basically, as far as I understand, like every time we call a function, it sort of puts it onto the stack of called functions. And if we call a function within that, it gets added to the stack, and it's not until the function gets resolved that we're removing it from the stack. So I think, like, I have to imagine that that would take up more memory than just doing a loop. But then again, I mean, I guess we have an extra variable in memory over here. So yeah, I really don't know. If anyone knows, let me know. As for now, let's see. Is there anything else left to be said about these? No, I don't think so. So, okay, here, let's move on from here. So we're going to try another attempt. And this, I think, is going to be the one. Okay, so at this point, we've looked at a number of ways of doing this. So we found we could do it with a loop. We could do it with arrays and like array built-ins. We could do it with recursion. Could we do it with using the power of math? You know, like we saw with the previous one, math really helped us out. It really made it look a lot more efficient. So, well, and not just look a lot more efficient, it made it more efficient. Like it allowed us to get a constant time algorithm. So I'm hoping we can get the same thing in this case. Can we get a constant time algorithm? Well, that's tricky, but let's give it a try. So first of all, I'm going to have to clear this. I forgot to clear it during the break there. Sorry about that. Okay, so what are we looking at? Well, basically, okay, we're starting with a times b, right? That's, and by the way, this is going to be kind of long, so consider yourself warned, I guess. A plus 1, b plus 1 is going to be the next one, right? And we're just sort of going to continue that pattern, a plus 2, b plus 2, etc. So that's going to sort of keep going like that until a certain point. Should we put, yeah, we might as well. A plus 3, b plus 3. Might as well. And I hate using b as a variable because it can sort of look like a 6. So watch out for that. And then let's just put a little ellipses here. How long is this going to go? Well, if n is, let's say, in this case it was 2, right? Well, in that case we found there was a times b, and then a plus 1 times b plus 1, and then that was it. So basically, it's going to go up until n minus 1. Okay, so we're going to have a plus n minus 1 times b plus n minus 1. Okay, cool. And then what are these things all equal to? Let's do some expanding and simplifying. Oh, that's going to be fun. Okay, so what do we get here? Well, it's just AB, A times B, we get AB. What about this one? Well, this is a little more interesting. We get some binomial expansion here. Hey, let's take a moment to actually figure this out, you know, why it's gonna give us what it does. Well, how long do we want to spend on this? Let's spend a minute on it. So, okay, basically, first of all, well, we gotta talk about the distributive property, I guess, right? So let's do this real quick. If we had something like 3 times 2, then that's going to be equal to 2 plus 2 plus 2, right? If we had 3 times A, oops, there we go, that would be the same as A plus A plus A. If we had 3 times A plus 2, let's say, then that's going to be the same as A plus 2. Whoops. And basically, like, all of this is just based on the principle that multiplication is really just repeated addition. I mean, that's sort of what it means, right? Like 3 times 2 is like take 3 groups of 2, add them all up. So that's basically the idea. Now, in this case, we've got parentheses around all these things, but we don't really need those. I mean, we don't need to change the order of operations because it's all addition, so we can resolve that in any order. So we can do A plus A plus A, that's going to give us 3A, and we can do 2 plus 2 plus 2, that's going to give us 6. And what we notice from this is that, well, basically we've just sort of proved the distributive property. I say prove, but, you know, this is pretty... That's really just an example. It's not technically a proof, but it's a proof of concept. Okay, so 3 times A, 3A. 3 times 2, 6. There we go. So that's our distributive property. Okay, so hopefully we can all agree on that. Distributive property, because I'm going to erase it. So, all right, let's get a bigger eraser for this. It's a big job. All right. So, we believe in the distributive property at this point. Let's talk about one more thing before we move on. So we want to do this, right? A plus 1. All right, let's look at this one actually. A plus 2 times B plus 2. The way I'm going to treat this is, since we already know about distributive property, I sort of want to treat the A plus 2 as though it was one number, because we know how to handle the situation where it is one number. You know, one number times a binomial, well, it's distributive property. We just did it, right? So we could do something like this. A plus 2 is going to get multiplied by B. A plus 2 is going to get multiplied by 2. And we'll see what we get from that. So we get basically B times A plus 2 plus 2 times A plus 2. Some distributive property there. And then look, we have another distributive property situation, right? The B can get distributed into the A plus 2, and the 2 can get distributed into the A plus 2 as well. So what are we getting from this? Well, basically AB, just putting those in alphabetical order as per the convention, plus 2B plus 2A plus 4. And there we go. Okay, so you might use something different in math class. I mean, this isn't the way we would always do this kind of thing, but again, it's a kind of proof of concept. It's an example, an illustrative example that shows us why we can expand like this. Now, you might have heard of like FOIL and stuff like that. First outside, inside last. And yeah, we could use FOIL here. We could use other stuff too, like one thing that's become like sort of popular in schools is to do this grid thing where we say, here, let's make a, yeah, there, cool. We've got a grid. And we'd say something like, we've got A here, we've got plus 2 over here, we've got B here, we've got plus 2 over here. Or just multiply these out. So we say A times B is going to give us AB. 2 times B is going to be 2B, 2 times A is going to be 2A, 2 times 2 is going to be 4, and we just add all those up. AB plus 2A plus 2B plus 4. Okay, so we've got some options in terms of how we can do this. Just going to do a bunch of undos, and there we go. So, okay, we know how to expand this now. We've looked at a few ways of doing it. I'm just going to sort of use shortcuts because, you know, writing with a mouse, it's not the most convenient thing. So, okay. for this one, we would have a times b times 1, b times 1, 1 times 1. So ab plus a plus b plus 1. For this one, we'd have ab. Well, we saw this one already, so we had 2a, 2b, and then plus 4 at the end. Cool. For this one, it's still going to start with AB, so maybe we're noticing a bit of a pattern on that one. And then we're going to have 3A over here, whoops, plus 3B plus 3 times 3, which would be 9. Okay, so this is going all the way down to this over here. Now, these are two trinomials. We could like fully expand this and it would be a real pain, to be honest. So instead, what we're going to do is we're going to treat the n minus 1 and the other n minus 1 as just like one number. That's going to be sort of the idea here. So we'll have a times b, the conventional a times b, like we have in all the others, plus n minus 1 times a, plus n minus 1 times b, plus n minus 1 squared. There we go. Okay, cool. So what are we learning from this? Well, a fair bit, I guess. I mean, the main thing is that we want to add all these things up, right? So we're going to look at this in a few different ways. We're basically going to say that we have 4 columns here. So we've got maybe we can look at it in more like 3 columns. So yeah, something like that. Okay, so before we go any further, we should probably ask ourselves, how many of these are we going to have? So we start out with like a plus 0, a plus 1, a plus 2, a plus 3, a plus n minus 1. So we're going from 0 to n minus 1. So there are n of them. Okay. So that's probably an important note. We have n many entries. So I'll just put like an n over here. Yeah, cool. All right, and then, well, what are we going to do with this? Okay, so first of all, if we're looking at this column, that's probably the most straightforward one. It's a times b, and there are n many of these, right? So it's basically n times a times b. Oh, did I say a plus b? I meant a times b. Anyway, point is, a times b plus a times b plus a times b, n times, we're going to have n times a plus n times a times b. Okay, great. Cool. What are we going to have for this over here? Well, basically, it's going to be, okay, so we're going to have, okay, first of all, we could sort of factor this stuff out, right? So instead of like 2 times a plus b, and where am I going to write this? I'll write it over here for now. We could just say like 2 times a plus b instead of 2a plus 2b. The opposite of distributive property, right? So just like we could distribute the 2 into both these and get 2a plus 2b, we could also common factor the 2 out of these. Okay, so it's basically going to be something like that. Let me know if you have any questions about that. I realize that might be a bit of a jump. So basically, we're going to have a plus b for each of these. We're going to have 1 times a plus b, 2 times a plus b, 3 times a plus b, all the way up to n minus 1 times a plus b. So basically, we're going to have a plus b, and it's going to be multiplied by the sum from 1, well, technically from 0 to n minus 1, which is the same as the sum from 1 to n minus 1. So it's going to be like 1 plus 2 plus 3 plus all the way up to n minus 1. And then all that is multiplied by a plus b. Okay. Now, I guess we should probably talk about how we're going to get this, the sum of the numbers from 1 to n minus 1. Well, I think we've done this before. Correct me if I'm wrong, but I think we've looked at this before, and I think when we did, it went something like this. So we sort of had like, here's 1, we're going to use rectangles, okay, and we're going to look at the area of it. There's 2, there's 3, and let's just go to 4. Just again, we're trying to get an illustrative example here. We're not necessarily trying to go for like a hard proof. So basically, my claim is that the sum of these numbers, so okay, the area of this rectangle is 1, the area of this one is 2, the area of this one is 3. So if we sum up all the areas, we'll get the sum of all these numbers. So if we want to know the area of this thing, well, it's kind of an awkward shape, right? It's not really easy to get the area of something like this. So instead, we're going to take another one of these and we're going to rotate it 180 degrees, and we're going to stack it on top, and we'll find that one fits perfectly into the other one. And so then from here, we can basically say, all right, well, this was n, right? So like in this case, it's 4, and like, you know, this one had a height of 1, it was the first element. This one had a height of 2, it was the second element. Height of 3, third element. Height of 4, fourth element. Height of n for the nth element. But then we also have this plus 1 over here, so that means this whole thing is going to be n plus 1. Okay, so basically that means the sum as I goes from 1 to n of I. Okay, so that's summation notation, big sigma. So we're taking this thing over here, and we find that the sum, well, the sum of 2 of them was basically n times n plus 1. I mean, that's the area of a rectangle, right? So that's for 2 of them. We just want 1 of them, so we're going to take that number, or yeah, that result, and we're going to divide it by 2 to give us just 1 of them. Cool. Okay, so that's a way we can add all these up. Now, what if we wanted the sum going not from 1 to n, but from 1 to n minus 1? Well, basically just replace the n's with n minus 1's, right? So basically this becomes n minus 1 instead of just n. And then here we'd have n minus 1 plus 1. Well, that's just n. So we'll put that in, and we're going to divide the result by 2. So there we go. We actually have an expression for this now. So instead of all this junk over here, we can just say n minus 1 times n divided by 2. Okay, I feel like I need to like move some of this around if I can, because it's kind of getting in the way. Can I do this? Like, is this just going to delete it, or can I actually move it with this? I guess it's just going to delete it. Whoops. Okay, maybe let's undo that. What does this do? No, it's just going to make a rectangle, I guess, right? Is there a way I can actually move stuff? Or is that not a thing? Well, okay, hold on a sec. This is scissors, right? Normally that would be like a cut. Could we cut and then paste? Is that a thing? Doesn't appear to be. Nothing to paste. All right, well, I guess we'll just forget about that. We have the proof. I mean, we saw it, right? So let's just continue. Okay, so basically that means this part over here where we had all this stuff, this part, well, that's basically the same as n times n minus 1 divided by 2. Cool. And we're multiplying that by a plus b. Okay, cool. Now we're getting to the tough stuff, okay? Because we've handled, well, none of this was easy, but this is the part that's really going to be, yeah, kind of tough. So basically what we have now is not just the sum of the numbers. It's not just the sum of like 1 to n. What we have here is the sum of the squares from 1 to n minus 1. Okay, so basically what we have is something like this. I'll use the sigma notation again. So we'll say I is, well, yeah, I mean, it's technically starting at 0 and going all the way to n minus 1 of I squared. Okay, and that's it. We're not multiplying that by like a or b or anything like that. It's just the sum of the squares from 0 to n minus 1. Folks, we need to figure out what that is. I mean, we were able to figure this one out. We got our n times n minus 1 divided by 2. We want something like that, okay? We want to get something that's like this, but for this. So, let's do that. All right, I'm going to start by zooming out. Let's just go over here, I guess. Yeah. Yeah. Okay, cool. So, what are we going to do? Well, there's a few proofs of this. There are a few ways to look at this. Some of them are kind of, I don't know. Some of them are kind of weak, to be honest. like they sort of presuppose the formula, and then they just prove that it works. What I want to do is actually derive the formula, but we sort of need to be, I guess, like a little bit clairvoyant for this. We sort of need to have an idea of where we're going to go with this right off the bat. So that's in some ways kind of unfortunate, but it's going to work out. It's pretty neat in the end, the way it works out. So let's see, where should we start? Okay, so let's start with this. Let's say we've got n plus 1, and we're going to cube this thing, okay? So n plus 1 cubed. Well, we could go through the whole process here, but I mean, basically, this is the same as n plus 1 times n plus 1 squared, right? Same thing. It's just multiplying this 3 times, so however we want to mix it up, that's fine. The n plus 1, we're going to just keep that n plus 1 for now. And then for the n plus 1 squared, let's square it. So we get n times n, so on n squared, we get n times 1, and we'd also get 1 times n, so that'll give us 2n. And then we get 1 times 1, so just plus 1. Okay, cool. And then from there, we'll expand and simplify this. So we'll multiply all of these by n, and then we'll multiply them all by 1, and then we'll add those up. So multiplying them by n, we would get n cubed plus 2n squared plus n, and then multiplying them by 1, well, that's a little easier. It's just the same thing. So n squared plus 2n plus 1. Okay, so that was the expanding. Now let's do the simplifying. So n cubed, well, that's the only one of its kind, right? It's the only n cubed term. We do have 2 of these n squared terms, though, so add the coefficients. So we have 3n squared plus n plus 2n, so that'll be 3n, and then plus 1 at the end. Okay, so n cubed plus 3n squared plus 3n plus 1. What was the point of that? Okay, good question. So let's try to put this into context now. So this is where things are going to get, I think probably a little bit interesting. What we want to do is basically we want to, okay, hold on a sec. So we're going to get to the sum of squares, but the way we're going to do it is to do a sum of cubes first. Okay, so we're going to do something like this as I goes from 1 to n plus 1. We want to know what's this going to be. Okay, so that's basically the idea. We want to know the sum of all these things. Cool. So how are we going to do that? Well, let's find out. So basically the idea is we know that n plus 1 cubed is equal to n cubed plus 3n squared plus 3n plus 1. So if we wanted to do something like this, well, probably our summation is gonna look something like this. You know, we can probably expand this out in the same way that we did over here. I suppose we could verify that though. Yeah, probably no harm in verifying that. Yeah, let's do that. So we want to go from 1 to n plus 1. So I guess, where should we do that? I guess I'll just cut this out for now. Yeah, okay. So we'll switch colors and we'll just put that stuff down here. So we have this, so that's probably going to help a little bit, maybe. We'll find out. Just to sort of, again, put this into context, this is n plus 1 cubed. Okay, cool. So then where are we going to go from there? Well, basically 1 cubed is going to be the same as, well, technically it's like 0 plus 1 cubed, right? So in this case, the n value would be 0. So, okay, basically that means it's 0 cubed, which is just 0, plus 3 times 0 squared, which is still just zeros. This one's not all that interesting yet. Plus 3 times 0 plus 1. Okay. Now, whoops, let's look at 2 cubed. Okay, so in this case, 2 cubed is the same as 1 plus 1 cubed, so we can say n is 1 in this case. So we'd have 1 cubed plus 3 times 1 squared, which, yeah, again, is still just 1, plus 3 times 1 plus 1. Oh, I meant to switch colors. Whoops. Here, let's do a fun little dividing line there. Oh, that was fun. Okay, so then we'll do 3 cubed. So in this case, n would be 2. 2 plus 1 is 3. So we'll say 2 cubed plus 3 times 2 squared. We're just starting to get a little more interesting, so that would actually give us 4 plus 3 times 2 plus 1. Okay, yeah, it's probably enough of those, and then we'll just do like a dot, 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 because we want to go all the way to n plus 1, right? So n plus 1 cubed. So in this case, well, it's just this. We already have it, right? So we've got n cubed plus 3n squared plus 3n plus 1. Nice. Okay, so we've got all that. Really, what we're concerned about, what we're interested in here is the sum of all these things. So if we're looking at the left side, then yeah, we're basically just looking at the sum of cubes. So this is where I goes from 0 to n plus 1. Or should we do it this way? I'm wondering if we should. Yeah, I guess so. Okay, so we'll have I cubed. Yeah. Okay, cool. So basically that's what we're looking at, right? I goes from 0, or more like 1, I guess. Yeah, I would feel better about using 1 for this one. So where's, oh, there's the eraser. Okay. Oh, and we're going to need a smaller one. Okay. So I is going to start at 1. It's going to go all the way to n plus 1. Okay, so, oh, geez, we need another dividing line over here. Okay, so how many did we have here? That's probably worth noting. So we start at 1, we go all the way up to n plus 1. So there's going to be n plus 1 of them. Okay, so unlike before where there were just n of them, we've got n plus 1 of them. So that's going to be important. Switch back to this, and yeah, let's take a look at each of the components here, I guess. So if we look at this part, well, basically we have another sum of cubes here, right? This one is a little different because it's going to start at 0 and go all the way to n, not n plus 1. So it's a little different, but ultimately pretty damn similar because, I mean, it's the same sort of thing. So that's probably a good thing, you know, all things considered. We'll probably make use of that fact. But for now, let's just take a look at what else we have. So this, well, we basically have 3 times 0 squared plus 1 squared plus 2 squared. So basically the sum of squares from 0 to n, which is kind of the thing we're actually looking for, right? So I'm sorry it took this long to get there, but this is ultimately what we're after. Right, we're trying to isolate this thing. We'll try to solve for it. Before we do though, let's just take a look at this part over here. So this is just the sum of numbers from 0 to n. Nothing squared about it or anything like that. It's just the sum of numbers. So just put an I over there. And then we've got a whole bunch of ones. How many of them? Well, n plus 1. So we're just going to add on a little n plus 1. Okay, great. So, nice and simple, right? Nice and simple. Just kidding. Okay, so this is looking kind of messy. It's looking maybe a little bit intimidating, but not to worry. We're going to do some stuff here that's actually going to clean it up a lot. So we're going to do a few... no, let's do one step at a time for now. Okay, so basically, the first thing I want to do is I want to do a bit of rearranging. I want to basically subtract from both sides the sum from 0 to n of I cubed. Okay, so basically this term right here. It's on the right side. I essentially want it to be on the left side. I'm going to subtract it from both sides. So we're going to have that sum minus this sum. Ugh, sorry about that horrible sigma. And I mean, something to note is that I'm saying this one is starting at 1, this one's starting at 0. It doesn't make a difference, right? Because 0 cubed is still 0, so that's not going to make a difference. Okay, and then we've got 3 times, yeah, the thing we're looking for, right? I goes from 0 to n of I squared, plus this thing over here, 3 times the sum of numbers from 0 to n, and then we have n plus 1 over here. I guess it doesn't really need to be in parentheses. I just wanted to sort of make it clear where it was coming from before, but yeah, this is fine. Okay, so here's where things are going to get kind of interesting. So we're looking at this part, and it's basically like a difference of 2 sums. So specifically, this one is going to be the sum of cubes all the way up to n plus 1, right? So for example, it's maybe going to be like 1 plus 8 plus 27 plus dot dot dot. It's going to go to n cubed, and then it's going to go to n plus 1 cubed. Okay, cool. And then from there, we're subtracting this one, which goes from 0 to n. So it would be like 1 plus 8 plus 27 all the way up to n cubed, and that's it. Okay, so then what we want to do is a big old subtraction here, right? So what's going to happen with that subtraction? Well, these are going to add to 0, these are going to add to 0, those will add to 0, these will add to 0. We're just going to be left with this thing. We're just going to have the n plus 1 cubed. That's it. It doesn't really look like an n. Okay, there we go. So all of this stuff over here, all of this big old complicated summation stuff over here, we can replace that with just n plus 1 cubed. That's it. And that's pretty nice. So I don't know, should I keep this on screen? Should I not keep this on screen? Any suggestions? I'm not sure would be better. I'll keep it there for now. Maybe we'll do what we've been doing, and we'll draw a little border. We'll section it off from the rest of this. So this is just a little aside. Okay, I need to zoom out, fit all this on the screen. So, okay, and it's probably gonna look like my text size is just gonna keep increasing, but oh well, who cares? So this stuff over here is the same as n plus 1 cubed. Let's get that in. On the right side, we still have this thing, this like summation business of the squares, right? So this is as I, whoa, hey, buddy. Let's do a better job. Okay, so as I goes from 0 to n of I squared. Okay, so that's our sum of squares right there. And then what else do we have? Well, we've got this thing. Now, you know, I've been thinking about this, and I think we've seen this before, right? This is just the sum of numbers from 0 to n. What we saw before is that that's the same as n times n plus 1 divided by 2. So we're going to treat it like that. Nice. Okay, that's great. And then we still have the plus n plus 1 over here. Okay, well, you know, we're getting somewhere. We're getting somewhere. What are we trying to do here again? We're trying to isolate this thing. So let's go ahead and do that now. We're just going to do some rearranging at this point. So we're going to say we've got 3 times this. We'll get rid of that 3 pretty soon, but it's fine for now. Okay, so we got that. And then, well, basically, okay, what I'm going to do is I want to get all this stuff on the other side, and then we're just going to flip sides, essentially, right? So what we would have to do is subtract this from both sides and subtract this from both sides. So on the what's now going to be the right side, we're going to have n plus 1 cubed minus this, okay? So that's minus 3 times, well, I guess we could expand that while we're here, right? So n squared plus n. And this is all divided by 2. And then minus n minus 1. Keep in mind to distribute that negative in the n plus 1 there. Okay, cool. So this is our sum of squares. We're almost there. Well, we're kind of almost there. Anyway, the point is, switching back to the pen here, what can we do with this? Well, we already have kind of an idea of what's going to happen, right? Like this over here, we've seen that already. That's just, it's like what we started with up top, right? Yeah. It was a simpler time. Our font was a lot smaller then. But anyway, n plus 1 cubed is the same as n cubed plus 3n squared plus 3n plus 1. So let's apply that down here. We've got n plus 1 cubed. We know what it is. Let's expand that. So we had n cubed plus 3n squared plus 3n plus 1. Shouts out to the binomial theorem. Pascal's triangle and all that. But anyway, okay. Let's continue with this stuff. So, how should I do this? I'll just keep the 3 there for now. Or should I? You know, that's a tough one. Okay, I think okay. Keep 3 there for now. But we're going to put it in the numerator. So it's going to be 3 times n squared plus n. All of this is going to be divided by 2. We've got minus n minus 1. Okay, and we're sort of getting to a point here where we could probably start to simplify some of this stuff. I think what I'm going to do, though, is just multiply both sides by 2, because it's bugging me that we have this 2 over here. So I might as well just keep writing in what we have on the left side here. I goes from 0 to n, I squared. Okay, so we're going to multiply both sides by 2 just to get rid of that pesky denominator. Now, of course, that means every term is going to get multiplied by 2. Okay, every term, so every set of numbers and variables separated by plus and minus signs. Each of those things is going to get multiplied by 2. So we got a lot of terms on the right here. So we're going to have 2n cubed plus 6n squared plus 6n plus 2. And this is nice. We can, well, okay. We could technically do 2 things at once here. It's probably worth it because the 2 is no longer going to be here. The 3 will be, so we can distribute it. So we'll say 3 times n squared, 3n squared. And then we're also going to do 3 times n over here. But keep in mind the negative. We do need to keep that in mind. So we're going to have minus 3n. Okay, and then minus n minus 1. Okay, cool. So we're almost there. What should we do next? Okay, we'll just keep this as it is, and then we'll just divide by 6 on the last step. And that's going to be a huge payoff. Okay, and that's I squared. All right, so let's just simplify this a little bit. So we only have the 2n cubed, no other n cubed terms. What about n squareds? We've got 6n squared minus 3n squared, so that's 3n squared. What about the n terms? And I actually forgot the n on that one, so nice save. Yeah, let's figure out what we're getting for these. Basically, we've got 6n minus 3n minus n. Oh, I didn't multiply those by 2. Whoops. Okay, my mistake. Sorry about that. Okay, so it's actually 6n minus 3n minus 2n, so it's just 1n. And then what about the constants? We've got 2, we've got minus 2, so that's it. Okay, cool. Well, this is really nice now. I mean, we're basically just about there. What can we do with this? Well, okay, let's divide both sides by 6. And it's going to be sort of like our big moment. We'll say that's going to be I squared. And yeah, basically we're going to have 1 divided by 6 times 2n cubed plus 3n squared plus n. And there you have it. Okay, so nice. That's great. This is a really nice closed form expression for getting the sum of squares. Okay, so keep in mind, we had a nice closed form expression for the sum of just the numbers, but the sum of the squares of the numbers, yeah, that's a little more complicated. So we could just go with this, or we could actually like factor it out. So the first thing we could do is just lift an n from all these, divide on an n from each of the terms, and then we would have like n divided by 6 instead of 1 divided by 6 times 2n squared plus 3n plus 1. And then, yeah, there's like a variety of ways that we could factor this thing. I'm going to go with like, I guess, a very traditional method. So I'm just going to say, let's find numbers that have a product of 2, a sum of 3, and the integers we get from that. So basically numbers that add to 3, multiply to 2. I'm thinking 2 and 1. Yeah, I'm thinking 2 and 1. Okay, so from here, got our n divided by 6. Whoops, n divided by 6. And then we're just going to break apart that 3n. We're going to make it 2n plus 1n because, well, those are going to add up to 3n. So this is called the method of decomposition, or basically decomposing this middle term into these other two over here. Why? Why would you do that? Great question. We would do that so that we can factor by grouping. So we've done a bit of common factoring. We're going to do more of it. So basically, we call this factoring by grouping because we're basically going to put these two into a group and we're going to put these two into a group. And because of the way we chose these numbers, because we know that they multiply to 2 and add to 3, we're going to find something interesting is going to happen here. So we're going to factor out the 2n. What's going to be left over? Well, n plus 1. Okay, so 2n squared divided by 2n is n. 2n divided by 2n is 1. Okay, and then over here, well, they don't really have any common factors, so this is just n plus 1. Okay, so then the cool thing that happens here is that notice the things we have in parentheses, these are the same. So since those are the same, that means we can factor those out. So basically we'll have our n divided by 6 out in front still. And basically what we have is 2n times some number plus 1 times that same number. So once we factor out the n plus 1, what we're going to be left with is just the 2n and the 1. We're adding those together. We get 2n plus 1. Nice. Okay, so that's it. That's the sum we're looking for. N divided by 6 times n plus 1 times 2n plus 1. But actually I kind of misspoke just now because that's not actually the sum we're looking for. It's very close to it, but what we're actually looking for is the sum that goes from 0 to n minus 1, I think. Let me find it. Ooh, wow. Yes, from 0 to n minus 1. So we're going to modify this a little bit. Well, not so much modify it. We're going to figure out what would we get if this was an n minus 1 instead of an n. That's pretty much it. So yeah, let's find out. Actually, you know what? Hey, might as well switch colors for this. It's a big moment. The sum from I equals 0 to n minus 1 of I squared is assign the value, or is equal to, sorry. It's going to be equal to, I guess I'll just do it like this. I'll put this here, and instead of an n, we're going to have n minus 1. Instead of n plus 1, well, n minus 1 plus 1, we get n. And then over here, we're going to have 2 times n minus 1. So that's going to be 2n minus 2 plus 1, so 2n minus 1. Okay, and yeah, I mean, we could equivalently express that as n divided by 6, just sort of, you know, putting them together in the fraction like we had before, times n minus 1 times 2n minus 1. Woo! Okay, we're almost there. So we have the thing that we need. We have the missing piece of the puzzle, and we want to plug it in right here. Okay, so we have that now. Let's see if I can do this from memory, and I probably won't be able to, but let's find out. So I'm saying this thing over here, and that's the same as n divided by 6 times n minus 1 times 2n minus 1. Okay. Okay, so that's a lot of stuff. We want to maybe consolidate that a little bit. So let's try that. So this thing, this is the big sum, right? Like this, all of it, this is the whole thing. You know, this is the actual number that we're looking for over here. So I don't think we have like a variable name for that, but we'll just use an equals for now, right? That's, you know, what we had on the previous line. So, okay, this is going to be equal to, well, notice we have a denominator of 6 for this one, right? We have a denominator of 2 for this one. We have a denominator, well, of 1 technically for this one. So what I'm going to do is I'm going to try to get a common denominator. So basically we're going to say 6 times n times a times b divided by 6 plus, I guess we need a 3 on this one to balance it out, right? 3 divided by 6 is the same as 1 divided by 2. So we'll say 3 times n minus 1 times a plus b. And that's all divided by 6. And then, of course, this part over here where we have n times n minus 1 times 2n minus 1. And all of that was already being divided by 6. So no major modifications to be done there. Okay, cool. So I know I keep saying this, but we're almost there. All right, check it out. So what I'm going to do now is basically take out the common stuff. We notice we have a denominator of 6 on all of these things. We also have an n in the numerator. I don't think there's anything else that's common to all the numerators, but we do have an n in there. So let's factor out n divided by 6. And that should make this a little nicer in terms of writing it out. So we're going to have 6ab. And then what else are we going to have? We're going to have plus 3n times n minus 1 times a plus b. And then, whoops, no, this n is not going to be there because we factored it out. So, okay, nice catch. There's the 3. Okay, and then what else? Well, n minus 1 times 2n minus 1. And I'll put the 2n minus 1 first because, I don't know, it's a bigger number. It's more intimidating. Okay, so here we go. And we got a large square bracket close up. Is that it? Could it be that simple? Let's find out, I guess. Whew, I'm nervous about this one, but yeah, let's give this a try. So we're gonna have n divided by 6 times 6 times a times b plus 3 times n minus 1 times a plus b plus 2n minus 1 times n minus 1. Can I remember all that? Probably not, but let's give it a try. So we want to return n divided by 6, and we're multiplying this by, I think I forget already. Let's give it a try. So I think it was 6 times a times b plus 3 times n minus 1 times a plus b plus 2 times n minus 1 times n minus 1. Okay, is that right? Did I get that right? Let's find out. 6ab, 3 times n minus 1 times a plus b, 3 times n minus 1 times a plus b, great. 2 times n minus 1 times n minus 1, 2 times n minus 1 times n minus 1, great. And we need to switch this to a 3 so that it doesn't actually get executed, and let's give it a try. Oh, that's satisfying. Okay, that is really a nice payoff, I have to say. After all that work, that is pretty nice. And okay, we've been talking about efficiency and stuff like that. It seemed like, you know, for me anyway, I was really conflicted on all 3 of these. I felt like these were all pretty equivalent. You know, they all iterated n many times. So I would say all of these were like a big O of n, you know, linear time complexity. And it's not really going to matter too much, again, because n is just, it's a maximum of 5. But what if it was a maximum of 5,000, right? If it was like a much, much bigger number, then, well, first of all, we would probably have to make it one of those ones where it's like, since the answer could be very large, give us the sum mod 1,000,000,007 or something like that, right? But if that was the case, if this did go up to 5,000, for example, or maybe a larger number, then we'd start to see a huge difference in terms of these ones versus this one over here. This is one step, no matter what. I mean, yeah, it's a lot of operations and stuff like that, but that's nothing compared to what we're going to have down here if this was like a 5,000 or like some other very large number. The point is, the time that this one is going to take to execute is not going to be significantly different at all, even if we give it very different numbers, right? We could give it like huge values of a, b, and n. We give it very small values of a, b, and n, and it's not going to make a difference in terms of the actual computation time here. So that's why we would say this is a constant time algorithm. And I gotta say, it feels good. I mean, we went through all this work over here. That's a lot. That's like a short textbook. Anyway, point is, we got it done. We found that there's a constant time way of doing this. I mean, yeah, we passed all the tests, right? I just want to verify. Yes, we did. Okay, cool. So, nice. Let me know if you have any questions, comments, or concerns. I realize, you know, maybe you came here for programming and you're finding that it was like an hour of math over here and it maybe seems a little out of place, but look, math is an important part of programming. Again, the way I like to think about this is, what if this was in production, right? What if this was like a web app or something like that? You wouldn't want it to have to take a much longer time to load if you give it a bigger number. If you can have a constant time algorithm, it's probably worth it, even if it takes some time to actually refine it to that point. Okay, so any questions, comments, concerns, suggestions? Let me know in the comments, I guess. We'll wrap it up there for now. So, yeah, nice job, everyone. That's great.